And this work is done in collaboration with my student, Niraj. And it came, my background has been in strongly correlated systems for a number of decades, but during the last few years, I have been talking to experimentalists here, in particular Baldikas. So we try to help them. And this came out of that attempt. So as a result, I'm going to talk about the role, at least in some basic way, of correlations in Weyl physics, how correlations can be introduced in a simple way, and this emerged out of trying to explain experimental data. It's not just an attempt to introduce correlations for no reason. So again, I will review very quickly because nobody discussed the Weyl semimetals this morning. So I'll do a very brief introduction on what Weyl fermions are and what it means a Weyl semimetal. And then I'll turn on my attention in transition method dichalcogenides, and in particular, I'd like to discuss, take an example, the gamma MOT2, and discuss what band theory tells us about the Weyl physics of these materials, and show the comparison with angular resolve photoemission. And then we'll see that actually there are some problems there, both in comparison with the angular resolve and in so-called quantum oscillation experiments. Our suspicion that something is incomplete there came from trying to explain the quantum oscillation experiments. But then if you go back and look at ARPES, you will see some problems there too. And so then I'll discuss very generally how correlations can play a role in Weyl physics, in what way they can play and what kind of role. And then I'll introduce the most basic approach to capture some correlations, which is to add the Hubbard U on GGA on this conjugate gradient approximation or any DFT other scheme to see what the role of these correlations will be in a basic way. And I'll do both bulk and slab calculations, and we will look in particular in polarization dependence of the light polarization in angular resolve photoemission, what it means and what are the differences, and we'll compare with ARPES this calculation, and we'll see that we can have a much better understanding of both ARPES and quantum oscillations with the same token. And we'll discuss the fate of Weyl points, because this was this became a controversy out of the quantum oscillation experiments, and we'll discuss what's happening, whether they survive these Weyl points with the introduction of this U. And we'll discuss the proximity to basically actually a couple of Lipschitz transitions, and then I'll conclude. Tomorrow I'm continuing. I have another set of transparency for tomorrow, but I think because this turns out to be a pretty long, today's might end up not being able to finish this whole thing. I may have to continue from where I will be left off today. So what are Weyl fermions in vacuum? This comes out from the study of Weyl, study the Dirac equation in a massless limit, and he realized that you can have this kind of Hamiltonian. It's a chiral massless fermion that we want to describe, and this Hamiltonian is not only producing Dirac cones, but they have the eigenstates have definite chirality. That means the projection of spin onto the momentum direction can be either forward or backward, and that gives this chirality notion that comes in with this concept of a Weyl fermion. Now on the lattice, I mean, when you do a real material, and this leads to semi-metal, and Weyl semi-metal is a crystalline material where it has states near the Fermi level, which are Weyl fermions, and those have they carry definite electric charge, and so we'll see that this has definite manifestations and different consequences in experimental physics. So don't expect the Weyl fermions to be like Dirac, like nice cones. They'll have the topology is the same, but they will have perhaps different mass, different velocities, Fermi velocities in different directions. But the main thing about them is that they occur in pairs. And so the reason for that is that this opposite chirality Dirac Weyl fermions are sources of and sinks of Berry phase, and as a result of that, because the net Berry phase across the Fermi surface, across the Brillouin zone has to be 0. You always have them in pairs, and this comes in high energy physics as the so-called no-go theorem by Nielsen and Ninomiya. Basically, what happens in their case, they try to put field theory on a lattice. They try to do any reasonable calculation. You have to regularize any field theory when you want to do calculations, and one of the most popular, because of the computational ability, is to put it on a lattice. Putting it on a lattice, you create a lattice gauge theory, but then you have to also, so you have a lattice, and at the end of the day, you have to, that's the regularization, you have to renormalize the theory in the continuum limit. You have to follow the beta function, and you have to remove this cutoff in a sensible way. But trying to put neutrinos on the lattice, it means there's a problem. And those are massless Weyl fermions. And so this is a statement by these two guys. But the statement actually is that you can't do lattice calculations for this type of objects. So it's a negative statement for them. For us, is that we are going to have them in pairs. Any questions so far? So today was this concept of Berry phase was discussed, and so I don't need to repeat that. I don't repeat it myself. So when you do a cyclic perturbation into an electronic system, that means, for example, you put an magnetic field, so you go back to the same state. When you have such a cyclic perturbation to any quantum mechanical system, you encounter Berry phase. Now, this cyclic perturbation in our case means a loop in K-space in Brillouin zone that comes back to the same point. So in that case, besides the dynamical phase that you come with any evolution of any quantum mechanical eigenstate, you have another phase, and that phase is defined by a Berry connection, a Berry vector potential A, which if you define which is basically the expectation value of kind of the dual momentum, if you like. It's not it's the derivative with respect to k in momentum space. So when you follow the Bloch state in momentum space, and then but you can rewrite this line integral in terms of a surface integral of the surface that's bounded by this closed path. And when you do this using Stokes' theorem, then you encounter, of course, the Berry flux, or the Berry curvature, which is the curl of this vector potential. But apart from the dual, transformation, this is corresponds to kind of a magnetic field, and this magnetic field is kind of slightly different from the usual magnetic field. It's a magnetic field of Berry flux, and it allows for magnetic monopoles, if you want, in some sense. Although in a solid, as I said, they occur in pairs of opposite chirality or opposite Berry flux, And in this case, in order to calculate the Berry flux or the Chern number, which is nothing but that divided by 2 pi, is to just enclose any of these topological singularities by a surface, just like you do when you apply Gauss's law, and integrate the Berry flux. Now, you're going to get something non-trivial once you have one of them. If you integrate over the entire Brillouin zone, you're going to get nothing because of this Nielsen-Ninomiya theorem. Another concept that comes, and another issue that comes in these things is that you end up with also Fermi arcs as opposed to surface states in the topological case, which are this. They are pieces connecting points on the surface, and this is, in fact, arising from the fact that you have topological singularities or topological charges, and the Berry flux has to emanate from one and be absorbed in the other, but you have determination. As a result of determination, those fluxes have to generate points on the surface from which they emerge, and so you have these things here. This is in one model, in two-dimensional model, how they look like. These models we'll discuss in the afternoon in the tutorial section. So these segments, these disjoint segments, start from the Weyl point. These are, this is a piece that you have cut in one particular direction, and you have the other directions being periodic. And as a result, on the surface of that fragmented slab, you end up getting a state. In this case, it's dispersionless for this model. It doesn't have to be dispersionless. And so you have two Weyl points at these two nodes. And so this Fermi arc emanates from one and goes to the other one. This is a periodic cell. This is a particular direction. So you have to think of this as being connected. It's not that there are two of them. There's actually two of them, but in fact, both of them are degenerate, and they come back and join the other Weyl point. What this second one shows is the wave function. Why are they surface states? If you study this and you calculate the wave function of these states, so if I pick one state here at a particular k-vac vector in this direction, then I can look at the wave function on the surface, and this is what you get for one state localized on one surfaces. The other surfaces, you get the purple wave function. But as I walk closer and closer to the Weyl point, what's happening is the wave function length, characteristic length, becomes bigger and bigger, and at the Weyl point, you get that kind of situation. And so that's because I'm approaching the bulk, but this is specifically for the Weyl point. Those Weyl systems have been observed in tantalum arsenic, and hopefully these transinstrumental dichalcogenides that Bernevik and others have studied thoroughly will turn out to be Weyl fermions. Our tentative answer is that they survive for these materials the test of correlations. And but you have two types of Weyl fermions. You have type 1, which is visualized like this. But then you can begin tilting the axis of the cone. And at some point, the tilting is such that if you have this zero energy level here, they begin sinking inside this plane. Here is this plane. This is, let's say, the Fermi level. And in this case, you have the top and the bottom cone inside and outside the Fermi level. And this is this crossover type of Weyl point where the boat is almost sunk. And this is the case where one of the boats is emerging from the Fermi sea and the other one is sinking inside the Fermi sea. That's a type 2 Weyl point. So differences in this case is that your Fermi surface here is, in this case, is going to look like two triangular corners touching with one another. Okay, and so it's this that MOT2, the gamma MOT2, is supposed to belong in this type 2 type, and we will discuss that. Oops. So what are the advantages? Why are these things, why people should study these materials? First of all, they have some degree of robustness compared to other things, because they are not of the other topological entities, because they are not sensitive to symmetries. They are accidents, bad accidents, or diabolical accidents, as some people are calling them. I was reading Witten's pedagogical lecture. He calls them bad points. So they don't depend on except on source of symmetry. They don't depend on other symmetries, and as a result of that, in condensed matter, they possess a high degree of mobility. And another property that they have is that they show anomalous transport, in particular negative longitudinal magnetoresistance. And I think Lewis is going to discuss these things in detail in the afternoon. He might even need 2 lectures to discuss all these recent experimental discoveries about these anomalies, this chiral anomaly. This chiral anomaly, which is the non-conservation of chirality, which classically is forbidden, but in quantum mechanics is allowed. Again, this is something that was very important in field theory, and it was Adler and Jakif, and then they discussed this in terms of this triangular loop coming in pion decays. And another reason why it might be interesting is because these materials could be a tabletop model to understand early universe anomalies. For example, we don't observe antimatter in large amounts. We don't have. They should have been equal if some symmetry is not broken, because as you know, out of vacuum in the beginning, the universe was only energy, and then out of these photons, you got particle and antiparticles coming out. And the question is, what happens to antimatter? I guess with a model similar to chiral anomaly, you can explain that the universe is now full of matter. This is something I always ask when I teach astronomy. You know, the students, believe it or not, I have to teach astronomy because we never had an astronomy department, but now we do. And so there I have to tell the students that, you know, I have to explain to them, where is this antimatter, what happened? So it can be a tabletop model to explain, to at least to simulate a complicated scenario of a universe which was very, very tiny, smaller than an atomic nucleus when it was emerging out of nothing, and it was all space and time was one point. Then you can always tangle the space and create all kinds of knots, which will be Weyl knots, and maybe the particles coming out from such, at least the fermions may come out of emerging out of this one scalar field. So when coming back to this real system, we consider this gamma MOT2, which is basically an orthorhombic phase, is in the 1T prime form, and we call it, we follow Bernoulli calling it gamma MOT2. And the lattice, the crystal structure has this kind of form. This is the unit cell. It's orthorhombic, the unit cell. You notice the spacing between layers, although we require 2 layers for the unit cell because of this inversion violation here. As you see, this layer is not, you cannot just go to this by just translating this. So you have to also flip it in a way. So that's our unit cell. And we'll consider that when we do calculations. So using this material, which is the sister to WT2, which is another transition metal dichalcogenide that we studied because of experimental interest, local experimental interest. So those sister two materials, which are orthorhombic, they have lots of Weyl points according to DFT. So let's see that. Let's see, first of all, the Fermi surface. But before I go to the Fermi surface, this is the band structure, and right at this point here, very close to the Fermi surface, a few tens of millieV above the Fermi surface, there seems to be a two touching points. Now, if you go into momentum space and you look at this, so you have two surfaces here. This is energy, and they occur at k is equal to 0, so I can plot them as a function of kx and ky, a and b, directions in crystalline axis. So I see that they touch these two sheets, energy sheets, touch at 2 points. And as they should, at least 2, there's more, there's 4 or 8 in this material, so 12. I'll discuss how they occur and whether they should be 4 or 2 or 8 later on. And so this is the situation for this. Any questions? Yes?
What's the color scheme in this? Why are sometimes colors different?
Oh, the color, or just to, you know, to make.
In the DFT.
Say it again?
In the DFT band structure.
Yeah, over here, you mean?
Yeah, yeah. So
The band structures? Oh, yeah, we just put them different colors because these ones are, you know, the valence, if you like, and the other one has the conduction state. Yeah. Any other questions? Yes?
What do you call gamma?
Oh, well, that's the name because there was already the alpha phase there was a beta phase, and this is a newly characterized phase, and it's this 1T prime is orthorhombic, and it's just a name calling. Yeah?
So the gamma phase is what people call something to do.
Yeah. Yes. Okay. Thank you. And so this is the DFT Fermi surface. Looks complicated. Has electron pockets, which are these purple ones, and the holes in this graph are these bluish. But it's more complicated because it's like the Russian dolls. There are within this, there's more Fermi surfaces. Within that, there is one more hole pocket, and so forth. And there are these other ones down here. And here is more expanded version of this. So you have, these are electron pockets, the ones that are designated with E. And as you see, these Russian dolls, there's more inside. There's structure in every one of them. So you have all kinds of frequencies, quantum oscillation frequencies. I'll discuss what they are because of all these handles and stuff like that. And so you have electron pockets, and then you have hole pockets nested. So it's a complicated thing. So in quantum oscillation, we'll expect plenty of frequencies to see.
Are you tuning your doping filter?
No. This is just pure bulk. Yes.
Oh.
This is this is for pure bulk. The Fermi surface, as you can see, you know, from this. Let's go here. From here, you can see all kinds of stuff here because orthorhombic, you know, you don't have any more the Kramer's doublet. They split, so you end up having all kinds of bands here. And so this is the hole pockets that you have 2 of them here and another 2 of them on this side, and the electron pockets. So they're very close to one another, but in principle, there are lots of them. And what this is showing is that there was a suspicion that something happens at low temperature. So Lewis had to go to Columbia to do some synchrotron to make sure that the 100K phase is the same as the 12K phase where the experiments were done. And so now, but let's look at ARPAS, right? People in the beginning, and I think Nandini Triverdi is going to tell you on Wednesday, I think, that there is good agreement. But when I look at these, what happens is that this is the DFT Fermis. This is from a slab calculation. Now, in order to compare with ARPAS, you have to do a slab calculation. And the slab calculation, of course, gives you Fermi arcs here. And this is the Fermi surface as seen by the calculation. Here is as seen by ARPAS. That's the gamma point. You can say, well, I see a good agreement. But notice that something, and other things also, that in this, around the gamma point is not luminous in ARPAS, and it's very bright in the DFT. And look at this gigantic hole pocket here, and look at these fragments and smaller hole pockets that you have. Also, if you are careful, you take a look at the polarization dependence. You say, well, here, this is for one type of polarization of light vertical to the surface, and this is horizontal to the surface. This is not bright in one polarization, and this is very bright in the other polarization. So if you like looking at these two, the disagreement is because this is not polarized calculation, and this is polarized measurement, and here you have, in the other one, there's more agreement, but you are missing these ears in this measurement. There are the ears here, but they are fainter here, and here they are bright. So what's going on? So we'll look at the polarization dependence also of this. So obviously there is something unexplained in these calculations, right? So let's look at these things. So what is this quantum oscillations? You'll hear about this from Luis, but because we can't put the cart before the horse here, well, let's just say what roughly they are. So what you're doing is you have a Fermi surface. Let's say this is this nice ancient Greek barrel or something, and that's the Fermi surface. And now you want to probe the structure of the Fermi, the looks of this Fermi surface. So what you do is you put a magnetic field. If you have the magnetic field along the z-axis, the electrons are going to go into the so-called extremal orbits of the Fermi surface. So here is one extremal, it's a maximum, and here maybe there is a minimum of the Fermi surface. You're going to get two frequencies in this case. Right? We have electrons going around, and because they are confined on the Fermi surface, otherwise inside the Fermi surface things don't move. I mean, there is no meaning because of Pauli exclusion principle. Only the Fermi surface is the one that reveals itself through quantum oscillation. So you can do these kinds of experiments, and you get frequencies. So these frequencies reflect themselves into some thermodynamic measurement of some observable. Let's say is the magnetization or something, or anything else, some resistivity or something where you have these oscillations as a function of the magnetic field. So if you plot them as 1 over the magnetic field, then the frequencies that come out from that, here is the fast Fourier transform. You could just get some frequency in some kilo, in this case is kilo Tesla, some field values for these frequencies. And if you use the Onzagier relationship, you can actually relate the frequencies to the area of this orbit inside the Brillouin zone. So you can calculate the area from doing measurements, believe it or not. And then you can tilt the magnetic field so you can see the variation of that orbit with tilting as a function of the angle. So basically you have a CAT scan of the Fermi surface by doing that. So we can map out the geometry of the Fermi surface by doing angular dependence of quantum oscillations. Make sense? Okay, so that's not, and it's a very sensitive probe because it's giving you details of the Fermi surface by doing this measurement. And so this is what you get. These dots are the experiment, and DFT gives you these solid lines. Embarrassment for DFT. That's where we come in this game. So, so what's the reason for this? Shall we believe DFT? So what we did in this experiment was to shift electron and hole pockets independently and be able to sort of agree here. So we brought this line down, it agrees with this, and we brought this further down because, and the hole pocket, so we're still a mystery that we had this thing here in the middle of this, but it may be, that may be a problem, as we'll discuss later, with quantum oscillations, not being able to probe sometimes some frequencies. Okay, so so here, so we have problems. One is the ARPES, polarization dependence, and the shape of the Fermi surface in general, and the second is this quantum oscillation experiments. And we claim that perhaps is correlations having something to do with this. What else? So let's take that point of view to explore it theoretically now, right? To explore that theoretically and see what happens. And so here is the, again, the DFT bands, but now we show the content of this and of these in terms of orbital content. That means D or P. Basically, the orbits, I mean, the bands that cross the Fermi level are mostly P or D. D, molybdenum D, and tellurium P. And here is the decomposition of them. This is mostly that. All other contributions are negligible. So what you see is that, for example, this one here, which gives rise to one size of electron pockets, is mostly D, molybdenum D. And very little of the size of these dots is the wave function square of contribution to the band, the wave function square of the D character. And the blue is the wave function square of the P character in that particular band. Make sense? So you can see that they are mostly tellurium P or molybdenum D. And so why am I doing this decomposition? Because I know D from my experience that the D orbitals are more localized, and so you're going to have, when you put two electrons of opposite spin on a D orbital, they will feel more this strong Coulomb repulsion. So one, in this case, needs to implement this U in the GGA calculation because every time you put electrons into this D state here, they will feel more repulsion. So on average, if you like, this state is going to be pushed up, even if you don't know anything, if you don't do any calculation. So that might be a way of explaining why we had to push things up and down to make the agreement with experiment, right? But let's be more quantitative. Be more quantitative. The other thing that you see here, since I'm on this figure here, is here is the Weyl point. If I move away from near the Weyl point, I have hybridization of this P and D, because that's how I produce the Weyl point, by hybridizing orbitals. If I move away, you can see here away there are D in this, and only, one is mostly D, this is very little D, and this is mostly P, and the other one is mostly D. So I can treat that if I want to have an understanding, I mean, by means of a model, I can add some U, some Hubbard U on the D and avoid putting it, or just to understand what's going on the other one. I can treat one as being pure D and the other as being purely P and see what's going on from such a model. Okay, so take a two orbital tight binding model, two orbital tight binding in any dimensions, It's going to give you, if you go to momentum space, it's going to give you a 2 by 2 matrix. This is the most general tight binding in momentum space matrix. It's a 2 by 2 matrix. Why is it the most general? First of all, it has diagonal elements which are real because it's Hermitian matrix, but they have K dependence. So you have the matrix element between A side, I mean D in this case, let's say call them A corresponds to P, P and P, this is matrix element between P and P, and this is D and D. They are momentum dependent in general because you can have direct hopping from an A orbital to another A orbital on another unit cell. You can have a long range hopping if you like. It doesn't have to be nearest neighbor hopping. So that's why I'm putting in general a matrix element which is a function of K. And the off-diagonal elements can be complex, but they have to be complex conjugate, the two ones, because that's a Hermitian matrix. So this is the most general one you can have, but I can immediately take out this average of these two energies. I can take the average out as an identity matrix and can be left in the diagonal elements by something which is the relative energy, but I have it here with a plus, and here we have the opposite sign. So I can do that always by some simple transformation. And then when I'm here, I don't care about this. Is an identity. This is not going to give me any. It's going to be just a center of mass movement of the bands of the two bands. But I have a matrix here which is not trivial, and I can rewrite that as my identity here. I can have some vector here dotted into a pseudo-spin vector. This is the Pauli matrices. This is because I have real and imaginary part. And the three components of this vector, one is this difference between the energy levels, between the diagonal elements. And the second component is the real part, and the third component is the imaginary part of the off-diagonal matrix elements of this tight binding matrix. Okay, that's very general. This is all you can have if you have two orbitals. And so in order to get a Weyl point, if you look at this, in order to get a Weyl point out of this pseudo-spin, this is not a spin. This will be a pseudo-spin related Weyl point. So, and I noticed that Bernevik's calculations and ours, without spin-orbit coupling, you end up with a Weyl point to begin with. The spin-orbit coupling doesn't create it. So it exists, so it's a pseudo-spin type of Weyl point because it exists without the existence of spin-orbit coupling. So this is what this tau is. So tau is a pseudo-spin, and up pseudo-spin means d orbital, p orbital, and down pseudo-spin means, if you like, the other orbital, d orbital. So you get, from the hybridization of p and d, you get the Weyl points. That's the point. But in order to get the Weyl point, this has to be 0. The Weyl point exists when there is a k value where this is 0, H2 is 0, and H3 is 0. That means you have to be able to simultaneously find kx, ky, kz equal to kx, ky, kz 0, some special point in k space where simultaneously I make this equal to 0, this equal to 0, and that equal to 0. And now, this is possible. It's an accidental thing, happens by some accidents sometime. So I have to solve these three equations to find kx, ky, and kz. So I have three unknowns. So that seems possible. If I'm in lower dimensions, though, I have kx and ky in 2 dimensions to be my unknowns. And I have 3 equations. So I have to be very lucky. The solution that I will find by solving these 2 in 2 dimensions to be the same one that makes 0 that one. And in 1 dimension, it's going to be even more. I have to be more lucky for such an accident. So as I go down in dimensions, the chance for an accident gets minimized. And in 0 dimensions, as you know, there is no accidents. If I stay home and I don't move, don't go nowhere, I will have no accidents. Okay? So how do I find these accidents? This defines a surface in 3 dimensions. Surface, just like the Fermi surface. This defines another surface, and this defines a third surface. So I have to have 2 surfaces intersecting first, and that will define a line. So I have 2 surfaces which intersect. Here is one surface. I don't know if you can see that. And as these 2 surfaces intersect, they define a line. And then the third surface has to come and cut that line, that closed line. And that's possible. It's not a terrible accident. So in 3 dimensions. So in 3 dimensions, I shouldn't be surprised if I find Weyl points, especially if I have a zoo of bands, and I'm in 3 dimensions, and my Brillouin zone is bounded. So I confine all of these things inside the bounded space, and I have lots of bands. So it seems that many material, I would be surprised if there is a material without Weyl points. The question is whether they are near the Fermi surface in order for them to play a role in anything. Make sense? Any questions? So now let me add to this general tight binding model with 2 orbitals a positive U only on the A orbital. So I add a positive U term on the A orbital. That means every time 2 electrons go to spin go on top of one another in the A orbital, they feel some Coulomb repulsion. And I'm going to treat this by mean field theory, right? What I'm going to do is I'm going to replace this product. These are the simultaneous coexistence of an up and a down electron on the same orbital A at the same site, R, same R. I'll do the standard decomposition, mean field decomposition, take the expectation value of this operator times that, or the other operator times that, and I'll pay the price by taking the average of both out, so that I can, because why am I doing mean field? Because all I know for topology is the one particle problem. I mean, it's one body problem, at least this topology that we are discussing. So if I want to do something more sophisticated, I have to look at quasi-particles, and I have to go to the spectral function and look at the residues there and see if they are non-zero near the quasi-particle pole, but they will have some width and stuff like that. And then I have to have a topology for this type of scenario, right? That's more complicated. And at the moment, I just want to, because I just want to help the experimenters, I just gonna do mean field theory. And that reduces the problem to a single particle, again, in the mean field of everybody else. Make sense? So I have the mean field of so the up spins provide a mean field, the density of up spins provide a mean field for the down spins, and vice versa. So I have to do a density functional theory if I'm gonna do that, by now having separated as a density functional theory with up densities and down densities separately. So I have to do a GGA spin, if you like, at least, in order to be able to treat that and do GGA spin and U on this. So, but I'm going to do the spherically symmetric version of GGA U when I do it at full phase, when I do the band structure calculation of this. But at the moment, I'm just doing a simple hand waving treatment in order to see what happens. So this now, all it does in my tight binding Hamiltonian is to add to the A part of the matrix, to this only part of the matrix, this term here, which is the expectation value of the down spins, if you like, or the up spins, as seen by the other of the opposite spin times U. So these people say, well, there are no correlations to these materials. It has a very low, it's not near half filling. Why do they say that? They say that because this expectation value is very small in this material. So let me just look at that. Here, the expectation, so the number of electrons occupying this band, or this band, or this band, is small. It's not like we are not anywhere close to half filling, like in correlated materials. So that is not half, it's some small number between 0 and 1. So one expects the effect of correlation to be small, because if you use any u, let's say you use u equals to 2 or 3 or 4 electron volts, and you multiply by 2%, you're going to get 450 millieV or something like that. But the whole energy scale in this problem, you know, this is, look, this is V, so from here is 0.2 eV, so this is 50 millieV, the whole thing. So yes, the correlations are weak in the sense that they produce a small energy effect in terms of pushing the bands up or down, but that's big enough for us because our physics is very low energy physics. These bands just almost cross the Fermi level, and then they have a very low. So the fact that the occupancy is low is consistent with the fact that the energy scale is small. So the two are together, so what comes in this matrix is the product. So this product, even though this is small, if the U is 2 eV, you'll get 50 millieV, no problem, with a U 2 eV, which is, nobody will question it for you if you use 2 eV as a U on the d orbital. Anywhere from 2 to 4 is no problem for the d materials, for the d orbitals to use. So now let's look at the one requirement. You have 3 requirements, 3 equations to make them 0. This must be H, not F. So you remember you have 3 equations. One equation is the difference between these two to vanish, so you have no gap, if you like, along some k. So you have to define a value of k at which these two dispersive matrix elements connect. That's the minimum. It doesn't mean that will turn out to be a Weyl point, because you have 2 more equations. So you have to close, first you have to close a gap. You have to make this equal to that. And if you look at this with u equal to 0, I mean, this is some schematic model. You have 2, this green is 1, let's say, E A of k, and this yellow on the bottom, this other band is less dispersive, so they cut and they define a line. Let's say it's not circular because my Brillouin zone is not, I'm not close to the gamma point in order to get circular. Let's say I'm getting some shape. But now if I put a finite u, I begin to spoil this. This is a minimal requirement. This is a necessary condition in order to begin having Weyl points. So if I put a u, I'm pushing only one of the two. Either here is what I'm doing by adding a u. I shift up this one of the two, if you like, matrix elements, diagonal matrix elements. So I shift it up, and I may not get an intersection. So even the minimum requirement might not be satisfied to get a Weyl point. So here is what's happening if I crank up u. So this is 0 u, this is, let's say, some moderate u, and this is a larger value of u. So at the moment, this is in 3 dimensions now, sorry. This picture before was in 2-dimensional model, and this is just the surface. This surface in 3 dimensions. I cannot plot E of k, x, k, y, k, z. Here I can plot E of k, x, k, y because I only am in 2 dimensions, and this is how the things I can pick. I have a picture of that, but in 3 dimensions, I can only plot the intersection, right? This is the intersection, that surface that intersects. And now if I crank u, this intersection becomes smaller, and then it vanishes at some point. But I don't have to make it disappear in order to lose the Weyl point, because I have the other requirements, which have to have, for the off-diagonal, the real part and the imaginary part of the off-diagonal matrix elements to vanish also. So here is, in the u equals to 0 case, And let's say this is the other surfaces that come from setting the off-diagonal matrix element. One of the off-diagonal, the real part of the off-diagonal matrix, I have an intersection here. So fine, I have some line here, which can be, for me, the place to have the third equation to come there and give me the Weyl point. So I have that, but for some slightly different value of u, because this shrinks, I lose that other requirement. So I don't have to have a huge value of u. I don't want to completely collapse everything in order to lose the Weylness. It's becoming sensitive to this u now. Make sense? Because I have three requirements to satisfy. So from this simple-minded study, what am I concluding? I'm concluding that about the role of correlations. I'm concluding that electron-Coulomb correlations can eliminate Weyl points, not right away with an infinitesimal u. You need some u to be, because they have some robustness. Robustness means that these solutions exist in a range. They don't just exist at one point, right? All these constraints are not satisfied. These constraints are not satisfied at one point in 3 dimensions. They are satisfied in a range. So if I crank up a u with an infinitesimal u, I'm not going to do anything. So I need to have a finite value of u in order to be able to disturb them and get them outside from the validity range. So I can eliminate pairs. They have to be eliminated in pairs, right, because of the theorem. They have to be eliminated in pairs. Or I can also create pairs. If these surfaces don't meet, by putting a u, I can push one and meet them. So I can, in the same token, I can create, I can eliminate, I can also create them. So, so as a function of u, if I thought u is have some crank which can change the value of u physically, I can create a quantum phase transition going from something which is topological to something which is not topological by playing with the value of u. Yeah. Oh, this would have been H1. This would have been H1. Yes, I said that. Sorry. Yes, that should have been H1. Thank you. Yeah, you are following. Have 5 minutes? Okay. Well, I'm glad I have another day. So. Lunch break is long, so you can go ahead. Okay. So, yeah, I have to discuss what's happening in the real situation. I have to do that tomorrow, including some analytical understanding of what's going on. So now we introduce, so I'm going to just show you what's happening when you introduce u briefly, and then I'll have to discuss the rest tomorrow. So if I introduce u with moderate value of u, let's say you have 3 eV here and 5 eV there, I have some small modification of the bands moving up or down, but one of the big effects is that these dots are u equal to 0, and the solid line is finite u. So one of the big effects is this pocket which is here and creating electron pockets. Electron pockets, they just go up because of this Coulomb repulsion. This Coulomb repulsion just moves this up, and the carriers that were here come down because you have to conserve the charge. The electrons that were occupying those states come down and fill the holes, right? And now the holes, because they get filled, they get the level, the Fermi level goes up, and the hole pockets become smaller, and the frequencies get smaller. This is immediate effect by just thinking. And so this is exactly what we did in trying to explain the experiment. We moved separately the electron and hole pockets, and many referees said, why are you doing these things? You were supposed to you had the only freedom you had when you want to fit quantum oscillation frequencies was just to move the global Fermi level up and down. No. So here is the Fermi surface shape. These guys go away right away with a very small value of u. We are losing these two guys over here. And the next thing that happens is that as you notice, this shape here, instead of being this, it just now begins to look like the experiment, which has some head and ears. Right? In the experiment, remember you had some head and some ears there? So this is just with u equals to 3. But when you put u equals to 5, you completely lose this connectivity between the ears and the head. And that's a Lipschitz transition. And experimentally, I think we are somewhere here because of attempt to free everything. We want to be faithful to the experimental results. So this is the picture that, as I'm going to show, that's going to be more faithful to both quantum oscillation data. Actually, we would have preferred this for quantum oscillations and this for RPES. But quantum oscillations can be also kind of happy with this picture. So, and then I have to do a lot of, to tell you about the polarization and other things. And I'll discuss that tomorrow because I don't have time today. But this is the Fermi surface story. Then the Weyl point story, I'll refrain that for tomorrow. Okay.
Well, any questions right before lunch?
I'm not sure if I misunderstood what you said last. So one of these figures, u equals to 2, explains the quantum oscillation data, and the other figure explains the
No, this is what we will adapt a value close between 2 and 3 as the one that, you know, this is not the perfect calculation. This is just the J plus U, right? This is missing a lot of things. So, but, you know, this is what we can do. I mean, we can do GW and other things, but calculating everything in terms of quantum oscillation and everything with GW method, there is, you know, we have to hack the codes, and we are doing all of these things, but, you know, we have also a limited amount of lifetime. And so we are doing GW. Within GW, if you want to have the best of both worlds, means RPES and quantum oscillations to be close, this is where we are. If you just want to ignore RPES, this is what we will prefer. That's what I said. But the point is that we are close to this Lipschitz transition either way. So quantum magnetoresistance might be huge because of the fact that the magnetic field will fluctuate the Fermi level slightly. And as a result, you're going to be having big changes in the shape of the Fermi surface by just small few Tesla magnetic field. So as a result, you will have huge different response. Plus, these pockets must be lurking near the Fermi level. Now they are inside, they're gone. But they are not too far away. They are maybe a couple of millieV below the Fermi level. So a couple of millieV or 1 millieV, you can have very anisotropic response because of the fact that any magnetic field is going to maybe pop out again, re-emerge these pockets, which are only in this direction. So one has to be careful when they think that it's the Weylness that generates all this anomalous transport, because here we're going to have directional transport. So one has to be careful that it's not this that's producing the anomalous transport, and it's the Weylness. One has to be careful because the Fermi surface is complex in this system. It's not a hydrogen atom. I don't believe it's a hydrogen atom of Weyl physics. This is a complicated system for it to be a hydrogen atom of Weyl physics. Yes?
I have a question on slide 9.
On
Slide 9.
slide 9? Wow. You counted the 9? Where is 9 now? Oh, okay, yeah. I see the numbers. Okay, yeah.
So this band stretch is calculated in some sort of ribbon geometry?
Yeah, this is this is some toy model 2-dimensional Weyl system that Niraj, my student, is going to explain the tutorial, and is going to give you the codes, these Python codes, how to do all of these things. And you will be able to do it actually by the end of the day yourselves, all of these things.
one last quick question.
How do we determine the U? We don't, we just. In ARPES? I'm sorry, what did? Oh, that's what I'm saying. We are varying it and just saying what is the value of U that's going to give us explanation of the real world.
Related question. So the band overlap is about 30, 40 million electron volts. On the other hand, the U is 5 electron volts.
With electron volt is absent in our scales here. We don't know what electron volt is in these materials. So half an eV, you go way away. Here is the val point. So so if you go like 50 millieV or something like that, you lose all the holes and all the electrons or something. If you crank a U of that type, you open a huge gap, and you don't have anything. You destroy everything. If you put a 10 eV U, so even though the occupancies, as I said, the occupancies of these bands is small, and so that's what counts. What counts is the effective repulsion from an electron when it jumps to a D band from the other electrons that occasionally visit that orbital. So you have electrons swimming from one orbital to the other, if you like, in a semi-classical picture, and from time to time they hop to a D side, but in the D side you have, it's a small room, and you're just trying to go to a room, to double occupy a room in a hotel, which is very small. So your energy will go up in this case as compared to a big room when you are going to go to a room in a hotel where there's another occupant, but it's a huge room. You can spread your legs and everything. No Coulomb repulsion there. So this is the effect we are talking about. The d orbitals are different from the p orbitals from that. In addition to that, the molybdenum is more isolated, as you can see, is shielded by two telluriums layers. So it's more isolated, more localized from the telluriums. The telluriums talk to each other, and whereas the molybdenum between, I'm talking about the c-axis, the molybdenums are caged, and so they are more localized. So if you go to small rooms, localized rooms, the correlations will be enhanced.